Okay, welcome everybody. As usual, we are going to talk today about finding the replication origin. And we will get to the tools to do, but the biological question that we want to solve is this one. And will lead us to other interesting biological questions that we will handle with the proper tools. Okay, we talked about this topic before in the class number 6. We say that essentially that the trick to find the replication origin in bacteria is to consider the GC-Skew, because in bacteria there is only one replication origin, and for a process of the way that the fork is built, there's sometimes part of the DNA that is exposed and you get mutations and so on. So how we can find this change of sign? We want to write a program. Essentially, I would like to program that you give a FASTA file, the name of the FASTA file, let's say, with the genome, and it will find the position where the chain, where the possible place of the origin of replication. Now, there are 2 points, no, because it's changed signs twice, because essentially there are two replicors, no, and one is the origin and the other is the terminus. We will find 2 places, and to decide which is the origin, that is a second step. But for now, we are essentially looking for the place that the replicors start and end. Core in this sense means body or part. So this is the part that replicates, the pieces it may be how the DNA replicates. And as we did before, we are going to do this using some kind of local statistic. And here is the concept that I want everybody to understand, because in previous courses, in previous years, people had trouble understanding this concept. The idea of going piece by piece. We like to call this window. Can be another name, but the idea that you have like the window, the one that you can open sliding. So you have a window that slide and you cover different parts, or you can see only part of the genome. It's like a window. You can see only one part, okay? So we would like to say something like the size of the window and the position of the window. And we did this before. We did this example. I just updated the drawing here. You have a different window. The space here should be 0. I make it bigger to be visible, but there is no, first, they don't overlap. They are not touching each other, and there is no gapples. They are side to side, okay? And we did some code. I make a little modification here just to make it in one function. In the previous class, we have a function and a function and a function. I want you to see and tell me if you understand how this works.
I think I understand. This is calculates only one part of the genome, GC-Skew, one part of.
Yeah. I mean, we had in class number 6, we had a function with the same name, same input and same output. The code was different, but the result is the same. I did a simple version.
I don't understand because of this positions mimic. It says circles. Okay, I get it, but which position is kind of make me hard to understand, because it's
what you don't understand about position.
It says from position, but which position? But
the position that I will tell you. Someone will tell you the position.
Okay. Okay.
Remember that there is a contract here, no? Between the person who writes the function, in this case me, and the person who uses the function, in this case you. We are going to calculate GC-Skew window by window. What is the window? Are part of the genome. They have a size from beginning to end of the, 300, 500, 1,000, 1 million, whatever. It can be big or small, but that is one parameter that tells you the size of the window. Is called size, okay? And then it can be at the beginning or at the end or in the middle, somewhere in the genome. That's called the position. Position measured in base pairs. Okay, evaluate GC-Skew window by window. That is what we want to do. Evaluate GC-Skew window by window. And to simplify things, I made a simplified version that take the position where we want to put the window, the size of the window, and in the last position, I'm taking the DNA, the genome or gene, whatever. This is probably going to be a chromosome. We make this, these are the indices from position, length, size that give you position plus 1, position plus 2, position plus 3, until you get size elements. We use these numbers as index of the DNA. So we get the letters in that position. You should not confuse, and this is important, you should not confuse the position inside a vector with the content of the vector. We make it uppercase just in case, it's just to make it uppercase. And I store that in V for vector, short name. And then this is the same code as before. We count how many times we see a C, we count how many times we see a G, and we just make a checking if these two numbers are 0. When don't make a division by 0, we just get 0. And if they are not, if the sum is not 0, then we can divide by it and we use the formula. So we need to, well, this is not very important, but essentially we need to have position, and we start from the first position in the DNA until the last. If you do until the length of genome, it will happen that the last, the window will be one that falls outside. You go, and one is falling outside. So I just did one before. Now we apply this function to everybody. And this is the point that I wanted to show. So this vector has different positions. Okay, the one that Khan was asking, where we will get this position? Well, they will come here. How they come? With this apply. We take remember, apply takes a vector, in this case, this vector of positions, take a function, and can also take other input that are passed to the function. So let me show you. The order is important here. This function has 3 inputs. The first input is position. The second is size. The third is DNA. Okay? Position, size, DNA. And here we put that function. The first value will be taken one by one from this vector. The second is fixed, is size, and the third is also fixed, is DNA. So these two are fixed. This change one by one, and we call the function one by one. And for every position, we call the function and we get the result. And that can be done in parallel. If you have many processors, this can be done in separate processors independently and it's very fast.
So the size is like if the window is for 3 nucleotides, the size is 3, right?
Exactly.
Yeah. Okay.
But in practice, we are going to be like 100,000 or 1,000. And the windows are probably going to be larger. There is the trade-off that if you have smaller windows, you have more of them because you have to cover all the genome. So the smaller window means more windows. So there is a trade-off. Okay, and we will talk about the trade-off. So we start with big windows just to show you the idea. Okay, I think we showed this result in class number 6. Size is 10 to the power of 5, meaning 100,000. For big numbers, I much prefer to use this notation because it is easy to understand that counting how many zeros. I mean, 10 to the power of 9, 10 to the power of 10, you easily confuse. So the origin will be in one of these points. Let's say one replicator ends here and the other ends here. There are 2 problems. One is that we have to find the places where the change of sign. That is a problem in itself. Which in this case, it was a little tricky, but we can talk about that later. It's not my point right now. The point that it is important is that we have 100,000 as the size of the window. So the real position of the change of sign is somewhere between half before, half after. We have a margin of error. So we have a big margin of error. So I am giving you the answer like let's say I'm looking for a person, I tell you, that person is in United States, which is true, but it's kind of useless because it's a big country. You need something that's smaller. How we can improve this thing? What will you do to get better precision here?
We can find exact spot that the GC scale change the sign. The exact.
But this is the plot. What will you do? Explain me again.
Create a function that calculates a scale, and we should find it where is it equals to 0. Then we should find.
Yeah, but in fact, it's never equal to 0. It is never equal to 0 because these are points. I draw a line, but these are points. And the only thing that you know is that here it is positive, here it is negative. Therefore, somewhere in between, it changes sign. But each of these points is a big point. They are wide. Maybe I should draw it with wider points.
We can shrink windows, maybe.
Yeah,
Get
that is the
smaller.
solution. You have to, I mean, if you are using kind of big pieces, your resolution is bad. The problem is that you have a bad resolution. You are looking like two big things. You need to see in more detail. You need to increase the resolution. That means having smaller windows. So we need to make smaller windows. This is what happens if you make the window smaller. Now we have, instead of 100,000, we have 10,000. Our margin of error will be 10,000. The window size is your margin of error because you are calculating the GCSQ in 100,000 places, and you don't know exactly the place. So if you make it smaller, you get better precision. But so where is the point that we change sign here? The change of sign is harder to see now. I mean, there are too many changes of sign. That is what happened in reality. We have to solve this problem. But on average, most of the windows in this part are positive. Here, most of them are negative, and here, most of them are positive. So it's not 100%, but most of them. And if you make it even smaller, 1,000, better precision, but even more noisy. You still see the pattern that are positive, negative, positive. But if you go one more, 100, you don't see the pattern here. It is there, but it's not visible with your eyes. Essentially, we have a trade-off. If large windows have a big margin of error, so we want a smaller window, but smaller windows are noisy. So it is harder to know where are we looking for. Where are we looking at? Okay, where is the proper change of sign? Most of the time, the skew is positive in one part, and most of the time it's negative. So we can take the sum. If we sum them, somehow positive will be more positive and negative will be more negative. So we're going to do that to find where the sign changes. We are going to do the easy way. That is the trick that I want to show you. Instead of looking directly to the skew, we are going to look at the accumulative skew. Okay, that we calculate like this. This is a new vector, and in the position I, you will get the skew I minus, but plus skew I minus 1 plus I minus 2, skew in I minus 2, and so until the beginning. Essentially, you take the sum from the beginning until the position I. The more you advance, the more you put. You get the idea? That's called an accumulative sum. You get different values, and you start summing from the beginning until the current one. This is an important idea, how we accumulate sum. This is, in fact, a super important idea. When people discover this, they change history.
But I have a question. There is 3 C's in the bottom code. Is it wrong?
No, I just pressed too much time.
Okay.
It was stuttering. Typing error. No. This is one less. How we calculate it? There are a couple of ways of doing it. I will show you the fast way, the same that we have supply. We have a function called cumsum. Accumulative sometimes is written cumulative. the dictionary take both options, accumulative or cumulative. This is the way you take the skew and you take, well, here I have one for a given size, and then I calculate accumulative skew. This sum is doing that, is doing this internally. Okay. Later we will think how we can make our own function. Our exercise today will be to simulate this idea. So just to give you the point, accumulative in the dictionary is explained like this. It's something that increasing quantity. Accumulative is the increasing. So for example, increasing, growing, mounting, aggregate. So for example, the effect of pollution are accumulative. You get, I mean, contamination, it gets things bad, and every day of contamination, it's getting things worse. They accumulate. Let's say if you smoke, you get a little damage in every cigarette, but they accumulate. You see here the original data, that is the noisy one, and the accumulated. You see what happened here?
The graphic is increasing, decreasing, then increasing.
Yeah,
like
that is a more interesting description. It's increasing, decreasing. Did you expect this? Will you get this idea?
I mean, yes, because it is increasing and decreasing. If you add positive numbers to positive numbers, it's increase.
Exactly.
At negative numbers, it's decrease.
So when you are adding it, if the most numbers are positive, you tend to increase. Sometimes you go down. For example, here you see here there's a little beep down that corresponds to this negative value here. But on average, it tends to increase until there is a point that things start to get bad and they go down, down, down. Well, I don't know bad or good. If it's COVID, it will be good. But you go down, 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 down until, and you realize what happened, that the maximum and minimum are the points where the thing changes. So we have a trick to use to find the change of sign. To find the change of sign, we don't look directly to it. We replace the problem of finding the change of sign, finding the zero, let's say, to do the accumulative sum and finding the maximal and minimal, the extremal values, let's say. That is a way to say maximum and minimum. It's called extreme. What is the maximum value? Or more important of what is the value is where is the value. I don't care so much of what is the value here or here. I care where in the horizontal position. Okay, I don't care very much about the vertical position of the maximum. I care about the horizontal position. That is the power of cumulative sum. Now we have to find where. How you find the where? Well, as I say, if you take the maximum, you will get a value like this. The value of the maximum is not really important. It will change. It will, I mean, I don't even know in which unit you are measuring it. What is more important is the horizontal position. Okay, where you get the maximum. How you calculate that? Be clear. What we are looking for is this position here. Not this value, 4 point something, this value here. In terms of the genome. We're looking for the position of the maximum, not the value of maximum.
We can say if xi is equal to 4.9877.
Okay, that is a solution. Like you get the maximum and then you want to find which one is equal to the maximum. Or you can use the function that we use in the homework. You can test the function with the following code, which.max. Which.max is the official function to give you the place of the largest value.
We can match function.
We can use the max function, or we can use the function that I'm showing you that is doing exactly what we asked it to do. Give me the index of the largest element. That is which.max. Look, function, which.max. What is the mean or max? Okay, which mean, which.max. Numerical vector, it will give you an integer. If the extremum, the minimum or maximum, is unique, the result is the same as the one that you are proposing, but more efficient. Well, this is another solution. But the easy solution, given that we have only one maximum, is to use which.max. Okay, this is an important point because many people get this problem wrong every year. Every year, there are people confused with this. For example, who is the oldest person in this group? We are 12 people in this session. Who is the oldest?
You are.
I am. What is who you know? Because I am. What is my age?
I don't know.
Yeah, you don't know, but you know that I am the oldest. I agree with that. So you don't need to know my age, the value of age, but you know who has the biggest value. But you get that the important point here is the difference between the value of the maximum and the position of the maximum. Notice the value of the maximum, it's a number with decimals. The position of the maximum is always an integer because it's the index of the maximum. It's an index inside a vector. It's an index inside a vector. It will give a pointer to point somewhere in the vector. Which vector we want to point? What is the problem that we want to solve here? That you can tell me. What is the problem that we're trying to solve here? What was the initial question?
Finding the replication origin.
Finding the replication origin. So that is what we want to do. And we know that the replication origin is located in one of these points, here, close to these points. And then we say that these places can be easily located close to the maximum or minimum. So the which.max and which.min will tell us something. But the problem is that the which.max and min are given an index in a vector and not the position in the genome. How we transform the index of the vector into a position in the genome? Okay, how you solve this question? You look at what you have here. First, start with what you have. What are the objects that we build here? We have a function that we use already, and we have some vectors. What are the vectors that we have here? Look at this plot. What are the vectors that you see in this plot?
ACC Skew.
Okay. What else?
The max and the min.
No, that is not a vector.
The win post.
Win post. What is win post?
The position.
Okay.
Vector for position.
It's a vector for position. And what were we looking for?
Replication origin.
The position of the replication.
Yes, position of the replication.
And where will be the position? In win post. It's the only thing that has position. We have three vectors. One that you see here in this skew line is the skew. That was the first vector that we make with supply. In fact, it was the second vector because the first vector that we make was window position. Where do you put the window? Window. The positions of the window. That allowed you to get the second vector with the skew, and then using that we got accumulated skew. We got this one. Then we get maximum and minimum, and we get the index of the maximum and minimum, and we have to use that index in which vector? If we are looking for the position, which of all these three vectors has a position?
Win post.
Win post is the only vector that makes sense. We have the maximum, we don't care. We have the position of the maximum, but okay, this is the index of the maximum. This is the index inside. And then we use that index to look inside win position. And here we got the position of the maximum, and we can do the same with the minimum. Okay, this is the position of the window that contains the maximum. Because the number makes sense. 155 is not really a position of a window in units of base page.
Why is it 155?
This is the first value. This is the second, the third, the fourth, 5, 6, 7, 8, 9, 10, 155. You count point by point, corner by corner, if you like.
Oh, okay, I get it now.
Okay. Remember, these are not continuous lines, these are points. I draw the line to make it easier to see, but these are points. So you go point by point, 1 point for every window. You understand?
I have a question. What will we do? But if there was multiple maximum and minimum?
Good question. Very good question. Then we can use the, if they are more than, it doesn't happen in this case. In bacteria, it doesn't happen. But if you are looking in archaea, for example, you will get more than one maximum, two with the same value. You can use this formula here that you have in the helper. Something which x is equal to the minimum of x. Because which mean give you a single value. This other will give you a list of all the points that are equal to the minimum or the maximum. Yeah, it's a good question. But in this case, we have a strong assumption that the values are, there is only one, I mean, they are global. That's a maximum, global maximum and global minimum. They're unique. Okay, in bacteria, that is true. So again, going to our argument. This is the index, and this is the genomic position. This is measuring base pairs. Therefore, what we know, let me rewrite. I assign to name to make it visually. So the place of the maximum is somewhere half below, half after. Here you see the margin of error. In this case, I use 10,000. But we can do with even higher. I mean, now we can use smaller windows. Let me just remind you again why we go to this. If we use big windows, if you use big windows, it is easy to find the place of change of sign, but the margin of error is big. If you use smaller windows, you get better precision, but more noise. To avoid the noise, what we do is find the cumulative sum with this function, cum_sum. We replace the problem of sign to a problem of minimum and maximum. And when we get minimum and maximum, we have different tools like which mean and which max. And that is a much simpler problem. So we essentially take a problem that is hard with a very noisy signal, and we replace it with a different problem that is much easier. Instead of looking for 0, we are looking for maximum and minimum, and a signal that is much cleaner. And we get more precision. Here we have 10,000 instead of 100,000 margin of error. But if we keep going further and further, let me show you. This is the original with 100,000. You recognize the plot, okay? And this is the cumulative one. Okay, we have a margin of error here. In fact, it's not very clear. This is the maximum, but this is very close to the maximum, so it can be anywhere else, anywhere in between. Now,
Fine.
Next one with 10,000. This is the plot that we showed a minute ago. You get this thing, cum_sum of skew. With 100, with 1,000, better precision, much more noisy. The original signal is much more noisy, but we still get the shape that we want, and the maximum is well defined. 100. You can go to 1. You can go down to 1 nucleotide and find the position with 1 nucleotide, the position of the change of. So just to finish this idea, the idea that we talked today is about accumulative sum, the command cum_sum. You can think in practical terms like this. Think about money. Every day you spend some money. Someday you receive some money, let's say. Let's say that you work, figuratively speaking, and you get paid, let's say 1 every week, like here, 1 every 7 days. So you get 500 liras every week, and then you spend some money every day. That is the flux of money. Positive when you get money, negative when you spend money. Income, weekly. Then my question is, if this is your income, sometime going in, sometime going out, what is your balance? How much money do you have today?
Maybe we can do this with sum.
Yeah, exactly. But in your real life, how you do, how you calculate how much money you have. But I guess you never had checks, but when you have a check, you have to calculate that by hand. In the old times, before online, banking computer, you have every check had a place to write the balance and the balance before, and you have to keep your own accounting of how much money you have in the bank. What do you think?
By summing the income and the outcome.
I mean, the outcome, the income, the outcome is a negative income, okay? So you take this, plus this, plus this, plus this, plus this, plus this, plus this. How you know the money that you have today? You check your pocket, but what is the money that you have today? How you get to the money that you have today? How do you get to today?
My mom give money.
Okay,
So I have money.
okay. And
So I use some
but
of
maybe
money.
you had money before. The mom give you 500 lira, let's say. But maybe you have some money before, no?
Yes.
So how much money you have?
I don't know. Do you want me to look?
Yeah, but it's, the money that your mom give you plus the money that you had before, no?
Yes.
And then you go and buy, I don't know, ice cream. You buy something. I don't know, cement.
Yes.
How much money you have?
I have less money.
The money that you had before minus the money that you spent.
Yes.
Or let's say plus the negative income. The money that you spent is a negative income. Okay.
Okay.
So basically, the money that you have now is the money that you have before plus whatever came in or out. Okay.
Okay.
In positive, out negative.
Okay.
I mean, I guess that this is what you do every day. How much money you have? Well, depending on what you had before and what changed.
Yes.
Isn't
Yes.
so?
Yes. Yes. That's it.
Generally, I use the bank that I used the application,
Okay.
and I learn by my niece.
Okay. But the point is that how you know that the bank is not cheating you?
I trust it.
Trust. Yeah. That is how people lose money.
But I can see my account summary.
Yeah.
And
but how you know that the summary is correct?
I don't know.
Understand. That is why it's important to know the basic thing that you start doing in life is to understand to sum and to take account. I mean, you go to buy in the corner. You are a kid and they send you to the corner to buy bread, and you have to know how to get the change, no? But in general, it's like basically the first reason why we teach arithmetic is to take account of it. Let's say that you are a shepherd and you live in the mountain and you have I don't know, goats or cows. Let's say cows or sheep. I don't know. You are going in the mountain and you have animals. You have to know how many animals you have. I mean, let's say you have 10 goats. They may die or they may have babies or whatever, but you need to know what happened. How many sheep you have today? Well, depending on how many you had yesterday, if any of them died or you sell one of the sheep, you have less. If you buy a new sheep or a new sheep is born, you get more. And the basic thing, how you know how many you have. But it's a basic moment of thinking how we know. The basic question that I always get is how you know what you know. How you know that the thing that you believe. If you trust the bank, they can make mistakes. I'm not saying that necessarily is going to be bad people, but people make mistakes. That things happen. And in particular, with money, the point is this: the balance of today. This is a summary. The balance of today is the balance that you had yesterday plus the income of today. Forget about this. The income of today. This is the basic rule that we have. Whatever we have today is whatever we had yesterday, plus whatever change. That change may be positive if we're things coming in, or negative if they are things going out. It can be money, it can be, I don't know, water. Let's say that you have a tank. Let's say that you are in a factory, and an industrial factory, and you have a reactor, and you are getting fluid inside and you're getting outside. Or less, more basically, how many people have COVID today? How many people are in the hospital today? Well, it's the people that were yesterday, minus the people who got recovered or died, plus the people who got sick. So what we have today is what we had yesterday plus whatever changed today. So balance and income here are vectors, because essentially, well, you can represent them with vectors because essentially it depends on the day. Okay, you have different income in different days, and you will like to track them, and they are connected by this relation of consume. We are going to use I. Well, can we also think, but traditional people use I to indicate the day. And you have not confused the vector income, which is the series of all days, with a particular element that is the value for a single day. So the balance will look like this in this case. You start with 500, and at the first days, you remember, it was negative. So money went down, and then you get more money, and is this plus 500. So got 600. This is a little more than 100. So here we have a little more than 600. And then it's going down again until you get more money. And that's how you get the money that you get today. If you know the income, you can get the balance. If you know the skew, you can get the accumulated skew. It's the same problem. And in general, if you know how things change, you can get how things are. The way that things are today is the cumulative sum of all the change that happened before. In fact, in the COVID website, in the one that we use, there is in the table that we used last was like daily cases and cumulative cases. You remember the column that we didn't use, but there is a cumulative thing. Exactly like this. We can calculate with the consume. Exercise time. Let's write consume, our own version. In the homework, you make your own minimum, your own maximum, your own which mean, your own which max. Now we are going to write your own consume. I have to say something. The homework that I give you are exercise of, I mean, they are practical. And in fact, they are so practical that most of the time there is already a function in R to do what I'm asking you. So there is, you are replicating something that is already existing. So the purpose of the homework is that you practice, is that you exercise with a problem that is easy. In real life, we will use the functions that are already made. They are faster and well tested and so. But we ask you to solve this question because it will help you to learn. Okay? So, how will you do that?